Good afternoon, dear students. So this is our class 9 of classical thermodynamics. So far we have studied about, in the last class we have studied about fugacity and the variation of fugacity with temperature and pressure. And one thing that we left unexplained during the last class was Lewis-Randall Rule. So we'll see what Lewis-Randall Rule is in this class. Lewis-Randall Rule states that fugacity of the species in an ideal solution, which may be a gas or liquid, is proportional to the mole fraction of each species in the liquid phase. If we are taking an ideal solution with components 1 and 2, if we are taking components 1 and 2, and we have fugacity of component 1 and fugacity of component 2, and the fugacity of component 1 is F10 into x1, where x1 is the mole fraction, and F2 is equal to F20 into x2, where x2 is the mole fraction of component 2. F10 and F20 are the fugacities of the components in the pure state. We are considering the solution, and F10 and F20 are that of the pure components before they form the solution. Generally we can write Fi is equal to Fi0 into Xi, where Xi is a mole fraction. How do you represent mole fraction? Ni by number of moles of component I by Ni in total number of moles, that is N1 plus N2 plus etc. Ni, total number of moles. Number of moles of component I divided by total number of moles of all the components will give you the mole fraction. Okay, this is the simplest form of Lewis-Randall rule. This rule is obeyed only when pressure tends to be 0. We are using fugacity when pressure tends to 0. The component is present in excess amount in solution. This rule holds good only for the component which is present in excess amount in the solution. The component which is present in higher amount, for that component only we can apply Lewis-Randall rule. And the physical properties of all components are nearly the same. There is not much variation between the physical properties of the components. That means if you are taking a mixture of two liquids, both of them must be equally volatile or equally non-volatile. It should not be that one is volatile and the other is non-volatile. Both of them should have the almost similar physical properties. Okay. Have you ever encountered an equation similar to this? In physical chemistry, you must have studied about Raoult's law. What is Raoult's law? The partial pressure of a component I in solution is equal to the vapor pressure of the pure component into its mole fraction. Okay, this Lewis-Randall rule is very similar to that of the Raoult's law, but Raoult's law is applicable to all ideal solutions, but Lewis-Randall rule is applicable to solutions in which these three conditions are obeyed. That's the difference between Lewis-Randall rule and Raoult's law. Actually, Raoult's law is a simplified form of Lewis-Randall rule. So this is all about fugacity and Lewis-Randall rule. So coming back to chemical potential, in a solution, the chemical potential of a component I, mu I, is given by mu I is equal to mu I star plus RT ln Fi. Okay, this we had derived during our class on chemical potential. Suppose that component is in the standard state. Then how will you write that equation? Component in standard cell state, you put a mu I 0. Okay. Mu I 0 is equal to mu I star, which is a constant, plus RT ln Fi becomes Fi0. First equation represents the chemical potential of a component in a solution, and mu I0, the second equation, represents the chemical potential of the component in its standard state. Now, if we subtract the chemical potential of the component in the solution, if we subtract the chemical potential of the component in standard state from that in the solution, we get mu I minus mu I0 is equal to mu I star and mu I star get cancelled out. What is left is RT ln Fi minus RT ln Fi0, and this can be written as RT ln Fi by Fi0. Okay. In this, what is Fi by Fi0? Fi is the fugacity of the component in solution, and F0 the fugacity, Fi0 the fugacity of the component in the standard state. And this ratio is now given the name relative fugacity. Relative fugacity, or it is also known as activity. Now, from fugacity, we are moving on to activity. So, what is activity? Activity is the ratio of fugacity of the component in solution to the fugacity of the pure component, or the fugacity of the standard of the component in standard state. Activity is the ratio of fugacity of the component in solution to the fugacity of the component in standard state. Okay. So, rewriting this equation, mu I minus mu I0 is equal to RT ln activity, which can be represented by AI. Okay. So, rearranging, mu I becomes equal to mu I0 plus RT ln AI. Now, we have chemical potential in terms of activity. Here, we have chemical potential in terms of fugacity, and now we have chemical potential in terms of activity. Okay, these two equations are very important. Now, let's move on to the details about activity. Activity is the ratio of fugacity of the substance in any state to that in the fugacity of the substance in standard state. For gases, the standard state is one in which fugacity is 1 atmosphere. For gases, Fi0 is 1 atmosphere. In such a case, activity and fugacity are identical. For gases, activity and fugacity are identical, and activity is only valid for liquids and solids. Whereas fugacity is valid mainly for gases, activity is valid for liquids and solids. Regarding activity, we have another term which is known as activity coefficient. Activity coefficient. This is because activity is very much related to concentration. These activity and fugacity are always considered in case of solutions, liquid solutions or solid solutions. This activity depends on the concentration of the solution. The ratio of activity to concentration is known as activity coefficient. AI divided by concentration is known as the activity coefficient gamma. Okay. Now, we know concentration is expressed in different terms. We can use either mole fraction or we can use molarity or normality or molality. Okay, all these terms represent concentration. The units of concentration determines what type of activity coefficient are we talking about. When concentration is expressed in terms of mole fraction, we can write activity coefficient gamma is equal to activity divided by mole fraction xi, and this is known as mole fraction activity coefficient. Gamma x mole fraction activity coefficient. When concentration is expressed in terms of molality, then we have gamma small m, and that is equal to AI divided by m. When concentration is expressed in terms of molarity, it becomes molarity activity coefficient. This molarity activity coefficient is known as practical activity coefficient also. In such a case, we will just write gamma I is equal to AI divided by C. AI divided by C. This is molarity activity coefficient. When you were attending the workshop on physical chemistry, you must have heard Prema teacher telling that in physical chemistry practicals, you have to use molarity when you are preparing solutions rather than normality, which you were using in degree classes. This is because of the fact that in physical chemistry, always the concentration, for uniformity, always the concentration is expressed in molarity. For uniform, in order to make the results uniform, we are always expressing in terms of molarity, and hence this activity coefficient is also known as practical activity coefficient.